Hello everyone. For the last video, I have discussed the fly-by-wire system overall and how it's implemented on Airbus aircraft, especially on the A320. And today, I just want to talk about how Boeing would implement their fly-by-wire systems on their pre-existing aircrafts, such as the 777 and 787. I decided to talk about 777 today because it is their first fly-by-wire system and also one of the more interesting ones with all different kinds of features. For example, there is thrust asymmetric compensation, which I will talk about later, which is going to be able to uh, reduce the workload for pilots when there is a engine failure. And also, of course, the flight envelope protection that protects the aircraft from leaving controlled flight, and many others. And today, I just want to talk about how the entire system works and how it is implemented to pilots and to its controllers. One thing to keep in mind about the Boeing 777 and Boeing fly-by-wire in general is how Boeing is keen on keeping their aircraft's handling to be similar with their older and conventional designs. For example, with conventional designs, which is aircraft such as 737, 747, 75, 76, they all have controls that have a different feel in different types of situations. For example, with conventional controls, when you're pulling back on the stick, when you're the more you are inputting in terms of control, the harder it gets. That it's physically more difficult to control or to pull on back on the stick when it's at higher speeds or at high angle of attack and other different kinds of situations. Boeing wanted to keep this feel in terms of control with the newer aircrafts, even if it is using fly-by-wire systems, which will not create such forces, as Boeing's have a very heavy focus on keeping the cockpit and design and also handling to be similar between all its aircrafts. That's also the reason why on the 737 the overhead panel is so similar from the initial versions from the 1960s always all the way to the 737 Max. In the modern days, it's all very similar because Boeing wants to keep their aircrafts similar in terms of handling and control. This is why they added a gradient control actuator, which is shown on the left of the picture, and it is a actuator under the flight controls under the cockpit in the actual aircraft that will mimic the feel and different forces of how the aircraft will handle at different situations. And also, very interestingly, with Boeing, the aircraft never would really ignore pilot input. That is one of the emphasis on the Boeing design philosophy to have the pilots always have control. So the gradient control actuator would also act in a form of flight envelope protection. For example, if you're going to be exceeding the stall angle of attack, the gradient control actuator will make the stick very difficult to move. And although it is still capable of being overcome by the pilot controls by applying a lot of force, it's a very clear indication to pilots that they're about to leave control flight. And also with other forms of, for example, roll. Well, when you are when the roll of the aircraft exceeds the optimal angle, the gradient control actuator would also make the flight control column very difficult to move. Another actuator under the flight deck, it's called backdrive actuator. With backdrive actuator, because it's a fly-by-wire aircraft and there are no physical springs that's gonna be returning the flight controls back to the neutral position or the neutral position that's determined by the fly-by-wire. There is a backdrive actuator that will be able to move the control columns back to neutral. And also there is a autopilot actuator. Because Boeing focus on allowing the pilots to physically feel and see how the autopilot is applying different forms of control. The autopilot input is always connected to your control column. So, for example, the autopilots want to do a right turn, then the autopilot actuators will also move the yoke, the control wheel, for the pilots to physically see that the input is being sent to the flight controls. So these are the features of the three different control modes: normal, secondary, and direct. With normal mode, there are all the features. For example, flight envelope protection, which is one of the most important features on a fly-by-wire system. I'll go in detail about the flight envelope protection later, but overall, it just protects the aircraft from dangerous controls. Secondly, there is TAC, thrust asymmetry compensation, which is automation where rudder trim is automatically applied when there is a thrust asymmetry, which is usually caused by engine failure. Wheel to rudder cross tie is a feature where the pilots are able to move the rudder with their control wheel, which is rather innovative. They won't be able to have full control authority with this feature, but they can move 8 degrees of the rudder either side in on the onset of engine failure, which can increase their speed in reacting to engine failure. There's also lateral gust alleviation, which I will also talk in more detail later, which can reduce the jolting and discomfort in at least in a lateral direction in a turbulent condition. There's also yaw damper, which is it's not really a new system on 777. It has been used for decades. It's a feature where it can prevent Dutch roll, uh, and allow the aircraft to have better handling. And also in normal mode, of course, there is the operation of autopilot, which can be used. In normal mode, the PFCs, which are the primary flight computers, are used. With secondary mode, which is a significantly degraded system, flight envelope protection is significantly degraded. And also, there are absolutely no uh, option of using the TACs, wheel to rudder cross tie, and lateral gust alleviation, yaw damper, autopilot whatsoever. Like all those five features are not operative with secondary and direct modes. However, there are still utilization of the PFC, although not much. With direct law, there are completely no flight envelope protection or TAC or all those features, and it will fly exactly like older aircraft without any form of fly-by-wire. So here are the flight envelope protection in more detail. The system can prevent a stall, and uh, there are two ways of achieving this. The first is that if the auto throttle is armed and the aircraft is reaching critical alpha, which is the critical angle of attack, the angle of attack which the aircraft will stall, then the auto throttle will automatically engage, if it is armed in the first place, and will set automatically for the minimum maneuver speed, which is the green dot speed on the Airbus. And also there are control column pressure. You cannot. It's significantly more difficult to pull back on the stick when you're near a stall because the gradient actuators with the flight controls will provide pressure. And this is one of the features on a Boeing where it is not really implemented on Airbus, and that is although you're capable of overcoming fly-by-wire systems, it's also very obvious that when it wants to tell you that you're in a risky situation. In terms of overspeed protection, there is a trim limit where the trim is automatically limited, where you cannot apply any form of trim that will lower the nose. This way, you will not be you'll not be diving and changing your potential energy into further, even more kinetic energy, which is usually speed. However, with the Boeing design philosophy, you can overcome it with alternate trim. Although most of the time in normal flight controls, pilots will not be using alternate trim. They will be using the trim switches on their flight controls. There's also a very interesting bank angle protection with the Boeing system. There is automatic return to 30 degrees when the aircraft banks, and also when it exceeds the 30 degrees uh, region, there is a control column pressure, just like the stall protection. There is also a PFD indication. On PFD stands for Prominent Flight Display, and for example, the indicator of how much the bank the aircraft has on the PFD will turn red or amber when the aircraft is in a large bank that it considers to be unsafe. There's also the rudder ratio system, but that is not really a new system on the 777. It's there for decades, and it just limits the rudder input, and it's like a variable that's controlling the like a modifier of your control into the rudders, your rudder controls. For example, at lower speeds, when you provide full rudder deflection, then the aircraft will actually give you the full rudder deflection. But at higher speeds, if you provide full rudder deflection controls, it might only move it by maybe 10% of how much it can actually move. This is to reduce the load on the vertical stabilizer. Otherwise, at high speeds, if you do a full deflection, the tail will just be ripped off from the aerodynamic loads. And I've talked about the TACs and rudder to wheel to rudder cross type, but here's just a bit more feature about it. With the TAC, there is a automatic rudder trim, and this will be engaged when there is an N1 difference of more than 10% for the two engines. The N1 is just how the RPM of the main fan blades on the engines. This eventually will allow for the ailerons to be allow for neutral aileron. So because during when there is a thrust asymmetry, there are two ways of dealing with it. The first is using rudder. The other way of using aileron. Uh, there's a saying uh that would that's usually utilized when there's an engine failure, and that's to bank towards the good engine. This way, the side slip will be able to compensate for the thrust asymmetry. However, this is not ideal. Usually, rudder is recommended for such situations, so the entire TAC system will aim for neutral aileron. Another feature that I just talked about is the wheel to rudder cross tie. It's just a convenient way for the pilot to deal with the onset of engine failure. However, it's only used under 210 knots because the higher speeds rudder control need to be it's very sensitive. As I've mentioned, a large deflection on the rudder can tear the tail off, and this have been shown with American Airlines A300 leaving New York a few decades ago, and that's also the reason why on the A300 nowadays there is a stop rudder input uh, display and also voice warning. And lastly, I want to talk about the gust alleviation system, which is one of the more innovative features on the 777. So this is a feature that's both on the 777 and also the 787. For the 777, it's only on the lateral dimension, so it's a lateral gust suppression system, where there are accelerometers on the nose of the aircraft, and also on the tail of the aircraft there are stacker ports. These will measure the pressure of the air around it, and eventually with the entire ADRU system, will work out whether if there is significant turbulence. And when there is, then it will provide automatic rudder input. This can be with or without autopilot engaged. So if you're flying without autopilot and you're just having neutral rudder control, if there's a gust of wind from the side, then it will also automatically provide input. And since the rudder is offset from the angle from the center of mass of the aircraft, there are also some automatic roll input in order to compensate it. On the 787, however, is slightly different. It's got this feature, but also has a vertical um, direction of control. So in the video, it's this is a video I filmed that shows how the flaperons on the 787 works with the entire gust alleviation system to increase the smoothness of the flight. Just keep in mind that it's slightly different because it does have some more features compared to the 777, but the principles are the same. So you can see the flaperons that are physically moving in the turbulent air, and this is can reduce the wing load and also to protect the passengers and crew from significant turbulence effects.